Morning class. We're going to do a quick little video here. I'd like you to watch and take notes. If you want to pause the video right now and try the warm-up, we'll go over it in just a couple seconds. Okay, let's go over this. So what are we asked? We have to find the equation of the tangent line of the function at the point x equals 3. Well, what do we need? We need to write the equation of the tangent line. We need a slope and we need a point. Right? Those are the two things that we're looking for. The point is when x is equal to 3, so I have to figure out what's the y value. Plug 3 back into the original equation, and then we just have to do some simplifying, and it's a little tricky here. If I plug 3 in, I get sine of 3 pi. So then we have to go to our unit circle and think, what is 3 pi? Well, 1 pi is halfway around the circle, 2 pi is all the way around the circle. If I go 3 pi is really the same as pi. So the sine at pi is 0. So then 3 times 0 tells me the y value is 0. So when x is 3, y is 0. We found my point, and I could basically plug x and y in right away for x1, y1. Then I have to find my slope. Well, what is slope? Slope is the derivative at the point that was given. So I have to take the derivative, and when I do the derivative, I have to use the product rule. So I want to find the slope at x equals 3. I'm going to take the derivative of the first, which is 1, times the original second, plus the original first times the derivative of the second. Now notice the derivative of sine is cosine, and then the derivative of the inside, this is a chain rule, then I have to multiply by pi. Now, I want to find the slope at x equals 3, so I'm going to plug in a 3 into the spot wherever I see an x, and then we have to simplify. So here I get sine of 3 pi, we already know that's 0. The cosine of 3 pi is negative 1. And then the 3 pi, notice this pi just came out in front, so 3 times pi is 3 pi times negative 1 from cosine of 3 pi. And then if I simplify, I get my slope at the expression x equals 3 is 3 pi, negative 3 pi. So my final answer then is just plugging those pieces in to the original equation of the tangent line. Y minus y1. Well, we know that y1 was 0. We just found that. They gave us x1. And then all I have to do is plug in my slope. And my slope was negative 3 pi. And then here, since this one is really friendly, we're just going to leave it like this right now. But I do want you to note one other thing that we could do is this is an approximation for the original function, right? F of x is the same as y. So we'll address that in a little bit here. So we are going to be using this process of writing the equation of a tangent line today to help us approximate the values of original functions. This is called linear approximation, and the key idea is if a function is differentiable, then it's locally linear, and I'll explain that with our first example. All right, let's look at this first example here. We've got the function, which is just a polynomial. It's a cubic, and it's positive, so it's going to look something like this. We don't really know, but it's going to be increasing from left to right. First step is we're going to find the derivative. So if you want to pause it at any point and work through these problems on your own, go right ahead. But what we're going to do is just take the derivative using the power rule. 3 is going to come down, take 1 away. 2 comes down, multiplies by the negative 2, and then the derivative of negative x is negative 1, and the derivative of 4 is 0. So here is my derivative. Right? Now, keep in mind, what is that? That's the same thing as slope. It's our equation for slope. And then for number 2, it says write the equation of the tangent line. All right, well, I'm going to throw in a little different notation here just to get you guys really comfortable with what we're doing. Let's think about this. What is what does all this mean? Well, I want the equation of the tangent line when x is equal to 1. So we know that x1 is 1, right? And then we know that the output is the regular point at 1. Well, I can find that. I'm going to do that up here. F of 1 is just plugging 1 into the original function. And then simplifying. 1 minus 2 minus 1 plus 4 equals positive 2. All right, so I'm going to plug those in a second, but there's our point, x1, y1. Now, the slope is the important piece, right? That's the part where we have to find the derivative, and it's the slope at the x value 1. So I know my slope equation from the first part. Now I can use that to find the derivative at 1. So we're going to take the derivative equation, and we're just going to plug 1 in for x. All right, and then simplify. And we get negative 2. So the slope, when x is equal to 1, the slope is negative 2. So now let's plug in everything that we know. And I get y minus y1. And what did we call y1? y1 was f of 1, which was 2. And then we have our slope at 1. So I plugged 1 in, and I had a slope of negative 2. And then I've got the point x equals 1. Now you could leave it like this. I'm completely content with this, the way this is written, or we can actually do one thing. And what if I add this 2 over to the end? I just want to show you a little bit of a different view on how you could write this. So y equals negative 2 x minus 1. And then instead of doing the minus 2, remember we just can add it to the end. All right. Now, there is a reason why I didn't FOIL, or excuse me, distribute here. And I'll show you that in a second. But remember, this is your equation for a linear approximation, or for the equation of the tangent line. Well, let's look at what does that look like graphically. All right, so I put up Desmos here, and you can see I graphed the original function, that's the red polynomial, cubic, and then I graphed the exact same tangent line right here. So let me just show you this quick. We're focusing on x equals 1, right? When x was 1, the point was 2. Now notice, when we say locally linear, what happens if I keep zooming in at x equals 1? Notice, the blue line and red line turned into the exact same value, which is kind of interesting, which means my equation for the tangent line could be used to approximate any value close to x equals 1. So, and that's our goal today, is now we're going to actually use the equation of the tangent line to find a value. So I'm just going to kind of pull this out here quick, and watch what happens. Use your tangent line to find a linear approximation for the point 1, 1. Well, one way to think of this is, remember, instead of saying y, you can think of that as f of x. So f of x is equal to the equation of the tangent line. And now we're just going to plug in 1.1. And you'll notice we're going to do this without a calculator. I'm going to actually use a different color here. So if I plug 1.1 in, we can kind of quickly do some algebra. 1.1 minus 1 is 0.1. And negative 2 times 0.1 is negative 0.2 plus 2, which is positive 1.8. So my approximation, now notice, I can't say equals, right? I mean, this isn't perfectly equal. I'll show you graphically why, but this is a very close estimate of what 1.1 is. Now, here's something I want you to appreciate. What did we do? We took the original function, and instead of plugging 1.1 in here, wherever there was an x, which is very hard to do without a calculator. Do you know what 1.1 cubed is? I don't, and I don't want to do the longhand math to find it out. But I do know that using the linear approximation, I can get a lot better answer. So let's think about what this looks like on my graph. Now, again, let's think about where we're at. If I have the graph, the part of my function, it kind of, and I'm not positive exactly how nice it looked, but let's say that this is our graph right here. All right, that's the original function f of x. And then I had a tangent line that we saw kind of went through here like this. And right at that point, the tangent line and the function were exactly equal. But wait a minute, we're not finding it at 1. We're at a point just past it, like 1.1. So our point is here when our actual answer is here. The equation, this tangent line is perfect when x is equal to 1, but when we're just slightly away from 1, it becomes an approximation. So that's the approximation sign right here. Right? Now, we're not going to be perfect, but this will get us close enough that we can feel confident that our answer is actually pretty close. Okay, so what did we just find? We found the approximate value at 1.1 of the original function f by using our tangent line. And we got 1.8. Well, let's compare that to the actual value. What if I took 1.1 and I plugged it into the original function? Notice, and I just did this quick on my calculator, I got 1.811. Now, look at how close we are. We are very, very close. In fact, our approximation answer is an underestimate because it's below the actual value by 0.011. Now, there's another reason why it's an underestimate. It's because the tangent line is below the curve, and that is something we'll talk about more when we get into it in further units. So that's the goal today. Now we're going to do a couple problems here. Here's another one. It's just kind of written differently, but the same information is what we're looking for. So you want to pause it and go ahead and try this, you may. Otherwise, here's what we got. What do they give us? Now they give us the derivative, right? That's really friendly. So they give us the slope. And they're asking us to write the equation of a tangent line. So we know what that is. Y minus y1 equals m times x minus x1. But again, in this case, notice the notation. They said dy dx, and we want it at the point when x is 1 and y is 0. So I'm going to actually use this extra little notation here. And then notice they already gave us x and y. So this is when x is equal to 1. And the output y is the notation f of 1, which we know is 0. So the only work I have to do for this is to find the derivative at the point 1 comma 0. But they gave us the derivative already, thankfully. So this is my side work. I need to figure out what is the derivative at the point 1 comma 0. So take your derivative. I know x is equal to 1. I know y is equal to 0. And then simplify. So we get 1/3 times 1. This is negative 2 squared, which is positive 4. And 4/3 is the slope at the point 1 comma 0. So now I can actually plug everything in that I know. I should have given myself more room here, but what do we have? We have y minus y1 All right, so what is y1? Well, y1 is f of 1, which they gave me as 0. And then I have my slope, which is the same as dy dx at the point 1 comma 0, and that was 4/3. And then I have the actual point x, which is 1. Now here you don't really have to do much simplifying because the 0 moving over doesn't really help. And instead of writing y, I'm going to write f of x is equal to 4/3 x minus 1. All right? That's my equation of the tangent line. That equation is really close, can be used for approximation for any value of x being 1 or close to it. Well, now look at, they want us to use this approximation, use the tangent line to approximate f of 0.7. So we want to say f of 0.7 is roughly equal to, it's not going to be perfect because this is an approximation. And then again, our whole goal is to do this without a calculator. 0.7. All right, well, 0.7 minus 1 is 0.3. Now, how do I do a decimal times a fraction without a calculator? Take the fraction and let's turn it in, or take the decimal and let's turn it into a fraction. Negative 0.3 is negative 3/10. And then here you can see the 3's are going to go away. And I'm left with 4/10, which is negative 2/5. And there is our approximation of our value using the tangent line. Now notice, it would be very challenging. We didn't actually even know the original curve, and you guys don't know how to turn this into a function yet. So this is the only way we can estimate or approximate values. Okay, let's try another one here. And again, pause this. If you feel like you got it, go ahead and pause it. But now we have a function, f of x, and we've got the point. And we want to find the linear approximation for the following function at the given x values, use it to approximate the function at the given value. So we're going to take the derivative, and again, we have to write the equation of the tangent line. And we know that this y value is the point. If x is equal to 0, the y value is f of 0. The point is 0, and then f prime is the derivative at 0. So I need to find two things. I need to find the derivative at 0, and I need to find the point at 0. I'm going to find the point first, because that's pretty quick. And again, we're doing all of this without a calculator. So here I get 1 plus 2 times 0, which is 1. And you should hopefully be familiar with the fact that the natural log of 1 is 0. All right, there's my point. I know what f of 0 is. F of 0 is 0. So the hard part, or the tricky part here, is finding the slope. I got to find the derivative at 0. What is the slope at 0? Well, here we have a chain rule. I've got my outside function is ln, so the derivative of the outside function is 1 over x, but the x is whatever's inside of the function. And I have to times that by the chain rule. So the chain rule is the derivative of the inside, which is 2. Or you can think of that as 2 over 1. Well, now I need to plug 0 in. I should have really called this f of x, because that's the derivative first. And now I'm going to plug in 0 into that spot and simplify. So notice 1 times 2, I can just put the 2 on top. And then I get 2 times 0 on the bottom. So I end up with, well, 2 times 0 plus 1 is just 1. Or my slope is equal to 2. All right, so now I have everything that I need. I've got my point when x is 0, I've got the slope when x is 0, and I've got the output when x is 0. And then you can just clean this up. The nice thing is the 0 doesn't go anywhere, and this 0 is just going to make it 2x. So this is my approximation function that I can use. Now here's the tricky part. You have to be very careful. Notice they didn't tell us what x is here. Use the equation line to approximate what the natural log of 1.2 is. Well, wait a minute. This isn't ln. And this isn't specifically ln. What we have to do is we have to take the inside part here. And I want to set 1.2 equal to the innermost part of this function, because that's what we're trying to approximate. All right, so now I'm just going to do some quick algebra. I'm going to solve, so I'm going to subtract 1, and I get 0.2 equals 2x. And then I'm going to divide by 2, and I get 0.1 equals x. Now, this approximation that I found here is whatever x is 0.1, we can plug it in. So my last step then is f of 0.1 is equal to 2 times 0.1. And then when I double, think of that as 10 cents. When I double 10 cents, I get 20 cents. And then this is my approximation. I should make this, I like the approximation. Now, how does that compare to the actual value? The actual value of the natural log of 1.2 now notice, I had to grab my calculator to figure out the actual value of 1.2, and it's 0.18232. And look at how close my approximation was. I used the linear equation, the equation of the tangent line, to approximate the value, and we're so close. This is an overestimation because it's larger than the actual value. Okay, so we got the last problem here, and I want to go fairly quick through this, so I wouldn't even write this one down. But let's look at what they give us. They give us f of 2 equals 6, and f prime of 2 equals negative 4. And then they want us to use this information to approximate what is the function f at 1.9 and 2.1. Well, let's think about what they gave me. They gave me a point. When x is 2, y is 6. So x1, x is 2 and f of 2 is 6. And then they gave me the slope at x equals 2. So what can we do? We can go right to our equation of a tangent line. And they give us the output. They give us the input, and they give us the slope at that x value. So I'm going to just go right to my equation of the tangent line. Here's my output 6, that's y1. My input is x1, that's 2. And then the slope is negative 4. So now, if I plug that in, remember, we just want to move the 6 over to the other side. And that gives me the equation of the tangent line, which instead of calling it y, we can call it f of x. Now that I know the equation of the tangent line, notice I didn't distribute the 4, that's okay. I can use that to approximate the other two values. So our whole goal is to do this without a calculator. So I'm going to go ahead and take my linear equation, and I'm going to approximate the value at 1.9. Which means I'm just going to plug 1.9 in, and then here's the part we can do kind of quickly in our head. We get negative 0.1. That has to times by negative 0.4, so that's going to give me a positive 0.4 plus 6, and I get 6.4. as my approximation for the function, which I think is kind of cool that we don't even know what the function f is, but we know that it's close to 6.4. Now notice, my original point was at 2.6, so less than 2 ended up being a little higher. Now let's check 2.1. All right, so we're going to take the same function, our tangent line, and we're going to plug in 2.1. Notice that just gives us a little higher value now. We get a positive 0.1, but then times by negative, it gives me negative 0.4, and that gives me 5.6, positive 5.6. So notice as we go past 2, my number drops down, and that tells us a little bit about a function. So there's the linear approximation. I hope you become really comfortable with this and kind of enjoy the process of using the point and the slope.